Today we're going to be looking at Unit 6. This is just a review, and our goal today is I will be able to review maybe notes 1 and 2. Alrighty. So if we look at this, the first little thing I want to look at is what exactly is a solution to a quadratic function. So just a reminder, solutions are where the graph or the parabola touches the x-axis. Now, if a graph touches the x-axis once, then we're going to have one solution. If it touches twice, then we're going to have two, and we're going to talk about those situations. So remember, solutions are also known as the zeros, the roots, or the x-intercepts. Alrighty, so if we look at this first one, our solutions to this function, this one happens to have 2 because it hits the x-axis right here and right here. Okay, so our first one is at -2, 0, and then our second one is at 0, 0. So this makes this quadratic have 2 real solutions, because it hits the x-axis 2 times. If we look at this next one, also 2 real solutions, so we're going to go ahead and label that one. And that's right there and right there. So you can also write your solution set. You can write this as coordinate points, or we can write this as a set. So we have one solution at -3. So in our nice curly brackets, we've got -3. And there's a solution at 1. So -3 and 1. Remember, your brackets don't have to be pretty. Okay, just as long as they're not parentheses, because this isn't a coordinate point, it's a set of solutions. If we look at the next one, this graph hits the x-axis at 1 point. So it has one real solution. And that is right at 2, 0. So we could label this at 2, 0, or we can write it in our solution set with the brackets. And then last but not least, this graph also has 2 solutions, one right here and one right here. Okay, because see, our x-axis is way up here. I know this graph looks a little different, but that's okay. So we have 2 real solutions. And then using my set notation, they happen at 0, and then they happen over here at 6. Alrighty, so we have 1 real and 2 real, but we also have another situation that could happen with a quadratic that we'll be talking about this unit. And that is a very special situation when what happens whenever it doesn't hit the x-axis. See, this graph never hits the x-axis. When that happens, that means this graph has no real solutions. It has imaginary solutions. So there are imaginary solutions to this quadratic, but there are no real solutions. And you'll talk about imaginary solutions when you get to Algebra 2, so get excited about that. Alrighty, so now we're going to be looking at our next little review section. And this is from the notes from yesterday about factoring and finding a greatest common factor. So when we're talking about the greatest common factor, the GCF, we're just looking for what is the biggest thing that these terms have in common. So if I look at number 1, I have 3x cubed minus 12x. The GCF of 3 and 12 is in fact 3. And then I have x cubed, so x times x times x, and then I have an x. They both have one x in common. Therefore, my GCF is going to be 3x. Then we're going to put all of our leftovers on the inside of the parentheses, and this is where we divide the 3x out of everything. So 3 divided by 3 gives me 1 with 2 leftover x's, so x squared. And then negative 12 divided by 3 gives me negative 4. I don't have any leftover x's here, therefore I'm done. Alrighty, let's do the same thing with the next one. I have 9x to the 5th y squared plus 12xy to the 4th. The GCF of 3 and 12, or not 3 and 12, sorry, 9 and 12 is 3. I didn't mean to make this GCF also 3, but it happens sometimes. And then we're going to break up our variables. So x to the 5th is x times x times x times x times x. Y squared is y and y. Over here we have just an x, and then y to the 4th, y, and y. And then we're going to box what they have in common. Well, they both only have one x, and then they both have two y's. So my GCF for this is going to be 3x, because they both have one x in common, and then y squared, because they both have two y's in common. And then we're going to put all the leftovers, so all the things that we didn't use, back in the parentheses. So 9 divided by 3 gives me 3. And I have 1, 2, 3, 4 leftover x's here, so x to the 4th. 12 divided by 3 gives me plus 4. And then 2 leftover y, so y squared. Alrighty, the last one for this little review section we have is 2x squared minus 4x plus 10. Notice that this 10 doesn't have an x. These two have x's, but this one does not. Therefore, your GCF will not have an x in it. It'll just be a number. So we think about the GCF of 2, 4, and 10 is in fact 2. They don't have any x's in common because this 10 doesn't have an x in it. Therefore, we can't take out an x. Therefore, that's our GCF is just 2. So 2 divided by 2 gives me 1. I didn't touch the x's, so x squared. Negative 4 divided by 2 gives me negative 2. Didn't touch the x. And 10 divided by 2 gives me plus 5. Alrighty, moving on. We're going to be reviewing some things from past units. So this is going to be review from Unit 2. We will need to be able to use this concept, so we're just going to touch on a few of these just as a reminder of what to do. So this is simplifying radicals, which like I said was Unit 2. So this should be kind of familiar. You might be a little rusty, but you should be like, okay, I at least remember using that square root. So if I have the square root of 24, which is my first example, okay, if I want to reduce that, that means break apart the radical. So step 1 says find the largest perfect square or cube root factor. So I want the biggest perfect square that goes into 24. So remember, our perfect squares are numbers like 1, because 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and then 6 squared is 36, and so on and so forth. So I want the biggest number out of this list that'll divide evenly into 24. Well, I know 36 and 25 are too big, so I can't even think about those. So next is 16. 16 does not go into 24 evenly. Therefore, I go to the next one. 9 also doesn't go into 24, so I go to the next one. 4 does though, which is good. So we can break this up into the square root, and instead of 24, now it's the square root of 4 times 6 gives me 24. Okay, so what I like to do here is then break apart the radicals, so I can rewrite them as the square root of 4 times the square root of 6. Okay, I just broke apart the radical. And then last but not least, the square root of 4 is in fact 2. So I rewrite it as 2. I can't take the square root of 6, so I just leave it as the square root of 6. And that's my final answer. Like I said, we've done quite a few of these way back in like September. If you're a little rusty, I totally get it. So that's why we're practicing. All right, so I'm going to rewrite my list of perfect squares up here just so that we have those handy. We've got 1, 4, 9, 16, 25, 36, 49. We won't need anything bigger than that, I don't think. So when we're looking at 40, I know that 49 is too big, so then I think about 36. Well, 36 can't go in a 40. 25 doesn't go in a 40. 16 doesn't go in a 40. 9 can't go in a 40, but 4 can. So we're going to rewrite this as the square root of 4 times 10. So then this is where I like to break apart the little radical. So I got the square root of 4 times the square root of 10. The square root of 4 is in fact 2. So I have 2 square roots of 10. That's my final answer. Do the same thing with the next one. I got 45. So thinking about 45, 49 is too big, so I can't use 49. 36 can't go into 45. Remember, if you're like, I don't know, can 36 go into 45? Type it in your calculator. 45 divided by 36, not a whole number, so you can skip it. So then I can try 25. Well, 25 doesn't go into 45. 16 can't go into 45, but 9 sure can. So I can break this apart into 9 times 5. This is where I get to break apart my little radical. Square root of 9 is in fact 3. So I got 3 square roots of 5. All right, we're just going to do one more. So we're going to skip down here to the square root of 12. So 16 is too big. So then we can check 9. 9 doesn't go into 12. So then I'm going to skip down to 4. So I can rewrite this as the square root of 4 times 3. I can break apart my little radical. So 2, whoops, not 2. What am I doing? 4 times the square root of 3. And then I can reduce it one more step because I know that the square root of 4 is in fact 2 square roots of 3. Alrighty, the last little section I want you to look at is what we call magic numbers. And we haven't actually talked about this before, but it's going to become really important tomorrow in notes number 2. So that's why we're going to practice this a little bit just to kind of get the hang of things. So when we talk about magic numbers, I'm asking what 2 numbers add to the first number but multiply to the second number. So when we look at 7 and 2, I'm asking what 2 numbers are going to add to give me 7 but multiply to give me 12. So what adds to the first number and multiplies to the second number. So if I'm looking at this, there are lots of numbers that add to 7. 1 and 6, 2 and 5. I could do negative 14 and 21 would also add to 7. Okay, so there are lots of numbers that add to 7. Actually, an infinite amount of numbers add to 7, which is crazy to think about. But anyway, there are only so many whole numbers that multiply to 12. So I like to think about the 12 first. So whenever I think about numbers that multiply to give me 12, the first ones that pop into mind are 1 times 12, 2 and 6, and 3 and 4. But if I think about these numbers, there's no way 1 and 12 can add to give me 7, so those cross off the list. Well, the next section is 6 and 2. Well, 6 and 2 don't add to give me 7, they add to give me 8, so really, really close, but not quite. So those don't work. And then I have 3 and 4. 3 and 4, though, when I add them together, give me 7. And when I multiply them, they still give me 12. So those are, in fact, my magic numbers. Okay, so my magic numbers for this scenario are 3 and 4. So let's move on to the next set. All right, so I got 5 and 6, so I want to know what adds to give me 5, but multiplies to give me 6. Like I said, there are infinitely numbers that add to 5, infinitely many numbers that add to 5. Therefore, we can't really start there, so we need to start with the 6. So what numbers multiply to give us a positive 6? Well, 1 times 6 and 2 times 3. Well, there's no way 1 and 6 are going to add to give me the 5. Therefore, I think about 2 and 3. Well, 2 plus 3, give me 5. All right. So 2 and 3 are my magic numbers. Alrighty, the next set's a little different because now I want to know what's going to add to give me 1, but multiply to give me a negative 30. So we have a negative number, so that means one of these numbers has to be negative, and that's totally okay. That's the only way we're going to get to a 1. So if we think about this, when we think about numbers that multiply to I like to just think about 30. So I've got 1 times 30 gives me 30. I have 2 and 15 gives me 30. 3 and 10 gives me 30. And then 5 and 6 give me 30. So there's no way 1 and 30 are going to add to give me 1. There's no way. 2 and 15 are not going to also give me 1. Even if I subtracted them, 15 minus 2, still going to give me 13. So those don't work. 3 and 10 aren't going to work because 10 minus 3 gives me 7. Not quite to 1. 5 and 6, though, are a little tricky. Or not tricky, they actually work. Because I'm trying to get to 1. Well, the only way to make 5 and 6 give me 1 is to do 6 minus 5. Okay, but we're adding, right? We want to know what adds. So that's why we're going to have 6 and negative 5. We think about it, 6 minus 5 gives me 1. So that means 6 times negative 5 is what gives me the negative 30. Alrighty, guys, so I want you to do these last sets on your own and then check your work with your partner, okay? And then you can move on to any homework that you need to work on.